Swayam Prabha. Digital India. Educated India.
In the last class, we have been discussing about excluded volume interaction, and we have been looking at what is known as a two-body interaction. And today we will take it further, derive the Virial equation that I have been telling you about, and then we go to the Flory theory that gives us the scaling laws for the good solvent case and the poor solvent case. Okay, so let's get started. So what we have covered earlier is the excluded volume interactions, which, if you remember, refer to the non-bonded interactions that depend on the physical distance between two segments as opposed to the distance along the contour that we have discussed in the ideal chain models. So the basic idea was like this. So if you have two segments of a chain, let us say M and N here, and of course this is contour variable going from 0 to M. In that case, we said that we can define the local concentration, that is the number per unit volume, as sum over all the segments, and a delta function of R minus Ri, and the delta function is defined in a way that if I integrate over the delta function over the entire space, then that is equal to 1, and delta essentially means that it is equal to a finite number when R is equal to Ri and it is 0 otherwise, and formally it has to satisfy the condition of normalization. So that essentially means that every time a particular segment I is at a position R, we add something of the order of 1 by V, and if I sum over all the segments, we get the numbers per unit volume, and that characterize the concentration or the number density, as you want to call it. And based on that, assuming that we have only short range interactions, that is, we exclude the case of long range Coulomb interactions. So short range interactions that decay rapidly, in that case we can approximate the interactions again by a delta function, and based on that what we have derived is the total interaction energy is given like this particular expression, where V is known as the excluded volume parameter, right. So you can do the dimensionless analysis here. So concentration is numbers per unit volume squared, so number square by volume square. We had a volume term here and we have a volume term here. So dr correspond to integration of dx, dy, dz in Cartesian coordinates. Okay. So now this particular interaction that we have discussed is basically what is referred as a two-body interaction. That is, we look at pairs of segments which can be nearby or at the same position if I approximate the interactions by a delta function. But in practice, it can be the case that three segments come together close to each other, and in that case we have to think about a three body interaction. Okay. So, the idea is something like this. So, now instead of just two, there can be three guys referred as say M, N and P. They are close together and they interact. This three body interaction is not the same always as the sum of the two body interaction. So, the interaction between M, N and P is not same as the sum of interactions M N, NP and MP, and this is what we refer to as a three body interaction. Okay. So, again, since we have assumed that this is not Coulombic, so we cannot take an example of Coulomb interaction really, but it is easier to think in terms of charges. So, if we have say two charges together, they attract, but if there are three charges together, then we form like what is known as a triplet of charge that is not the same as the sum over three doublets. Okay. So, we can extend the idea also to short range interactions, and this is what is referred as a three body interaction. So, in this particular case, we can extend the derivation we have done earlier for two body interaction, and note that now for the three body case, so let me refer the earlier one as two body. Just like we have done earlier, now we will have something of the order of so here we have a CR cube in place of CR square, because now we are looking at product of three delta functions as opposed to two in the case of a two body interaction. And then in place of two, that was for double counting of pairs, we have 6, that is all possible combinations of three segments. Essentially it is 3 factorial, and then we get a new parameter W, and we will talk about that in a moment. So, essentially then if I account for both of these, then we get and in fact, just like we talked about a three body interaction, we can think of like the 4 body interaction, 5 body interaction and so on. And as we go to say a 4 body interaction, we will have c to the power 4 in that, if 5 body interaction c to the power 5 in that. So, essentially what we are writing is sort of a series in powers of the concentrations. Okay. And this is what is known as a virial expansion, that is one of the most common tactic in thermodynamics to look at the interaction between objects. Okay. So, now one thing to note here is if the interactions are short ranged, then if I go to the higher powers of concentrations, we will get smaller numbers. The two body is more dominant simply because there is more possibility of having pairs as opposed to triplets. Similarly, there is more possibility of having triplets as opposed to 4 objects segments together, or quartets, so as to speak. And so, it must be like a decaying series. It turns out that this is not the case when we have like long range interactions. it does not form like a decaying or convergent series, and that is why we have kept the Coulomb interactions out of question. It is only true for short range interactions. So, we will use this particular expression in addition to the elastic energy of polymer chain that we have derived earlier to build what is known as the total energy of the chain. So, this is the interaction due to non-bonded interactions or excluded volume interactions, and then we also have some elastic energy purely due to entropic reasons, because as the number of segments increases, the number of conformations increases, the entropy increases. So, essentially it is a competition of two interactions in the system. We can think of excluded volume also as enthalpic interaction, and if you remember from thermodynamics, we are interested in quantities like Gibbs free energy change defined as the change in enthalpy minus T delta S, where delta S is change in entropy. So, this will come from the elastic energy and this will come from the excluded volume interactions. Okay. So, now we will discuss what is known as the Flory theory based on this particular idea. Before we do that, I want to remind you that the parameter V is a function of the solvent nature, as we have discussed in the case of water extensively, and it is also a function of temperature, simply because as we raise temperature, the entropy is increased and the interactions weaken, particularly hydrogen bonds, as we discussed in the case of water as a solvent. Okay. So, we can define the parameter V as some constant multiplied by 1 minus theta by T. This works in many cases, and this will be of course equal to 0 at T is equal to theta. This explains why we call ideal chain as a theta solvent. And of course, this will be higher than 0 for T higher than theta. This is what is referred to a good solvent, in which case I will get a swollen or stressed chain, and this is also referred as a self avoiding walk. And then finally, it can be less than 0 for attractive interactions. For T less than theta, this is known as bad solvent, and this is give rise to collapsed chain, which is having very smaller value of size than compared to the ideal chain and of course swollen chain. Okay. So, what we will now look using the Flory theory is we will look at the size of a chain, but we will not do it very rigorously. We will make what is known as an scaling estimate. Okay. So, in place of looking at the end to end distance or the radius of gyration of specific conformations and then doing an ensemble average, we will characterize the size of the chain as some quantity r, which of course correspond to the ensemble average in a rigorous description, but since we are doing I would say an approximate scaling theory, we are not doing a very rigorous kind of derivation. So, we will basically refer to some measure of size of the chain. You can think of this R being the square root of the mean squared average of radius of gyration you can also think in terms of end-to-end distance. Frankly, the way the theory is being built does not really go into details about what exactly the size is and how it is defined. It characterizes, I would say, a characteristic size of the chain and how it is changing with solvent. Okay. So now, with this in mind, we can now start building the total energy of the chain in terms of the two interactions we have discussed. One is the elastic energy and one is the interaction energy. So, I can say total energy of chain. By the way, we are now doing a Flory theory, and we are first doing it for the case V higher than 0, that is good solvent. So, total energy of the chain U is comprised of the elastic energy and interaction energy due to excluded volume that we have just derived. So, now there is a small detail here, that whenever we say that the energy is sum of the two contributions, we are actually making an approximation that is known as additivity approximation, which is not again rigorously valid. Okay. And the reason is this, that if for example a chain has a non-bonded interaction, then the elastic energy will not be same as that in the case of an ideal chain. It will not be as stressed as the ideal chain would, because it has either a repulsive or an attractive interaction. So, basically what it means is the elastic energy is not completely decoupled with the interaction energy. Okay. So, in reality, by writing any kind of these expressions, we are excluding any sort of coupling between two different types of interactions. The other way to think about it is in terms of degrees of freedom. So, the elastic energy will give rise to certain degrees of freedom of chain. So, we can do some kind of an stretching that correspond to a degree of freedom. We can also do at a level of a segment. So, those degree of freedom do not really depend on the interaction energy as well, but what we say is the degree of freedom because of elastic energy is independent of the degree of freedom due to interaction energy. Okay. So, we are not going in details here, but this is one of the first approximation that Flory made in his theory, although this is not the most serious one. We will come to the most serious approximation next. So, now what Flory said is the elastic energy is the same like it is for the ideal chain. Okay. Which means that the elastic energy scales like R square by NB square. We do not worry about the prefactors here. There was a prefactor of 3/2 if you recall. Since we are doing a scaling theory, we do not care about the prefactors. We only care about how the R scales with N or M. Actually, we are using M always. So, let us go back to M. Okay, M is the number of segments. So, although the chain has a non-bonded interaction, we still are thinking of it as having the elastic energy component same as that of an ideal chain, and then separately we look at the excluded volume interaction So, here again in fact we should do the integration that we have discussed earlier, that is right here. We will make two approximations to make things easier to avoid any kind of integration. The first approximation is V is higher than 0 and the first term is much higher than the remaining terms. So, we only consider the first term to be the dominant term and we will drop everything else from here. That is the first approximation. The second approximation is we will not worry about the connectivity of the polymer chain for the purpose of considering the excluded volume interaction. So, what this means is, of course, my chain looks like this. It occupies some volume. The volume, of course, in 3 dimensions scale like r to the power cube. You can think of it like a sphere has a volume of 4 by 3 pi r cube. We do not care about prefactors again. So, the volume is scaling like r to the power cube, and in that volume I assume that the segments are uniformly distributed. That means we do not care about the fact that the actual polymer chain is connected and it is not same as a uniform distribution of segment. Other segments cannot be like anywhere, it has to be connected to the previous segment, but we assume that this is the case. We assume that these segments are present in this volume and there is no connectivity between them, and in that case we can say that the concentration is actually uniform. That means concentration is same everywhere, and then it must go like m by r cube, that is the number of segments per unit volume. Again we do not care about the prefactors. Okay. So, we ignore connectivity. So, before we go further, let us look at like what sort of errors we are making here. So, as I already said that an ideal chain and a self avoiding walk or a good solvent chain case polymer chain differ in the stretching of the polymer chain, and in the case of the self avoiding walk we can expect that the chain is more stretched. I will use the abbreviation SAW. So, chain is more stretched. So, if the chain is more stretched, then the elastic energy, if I really would have considered the non-bonded interaction, would have been higher, and in fact by assuming it to be an ideal chain we are underestimating the elastic energy. So, this is underestimated. Similarly, here when we assume that the concentration is uniform, basically what we are doing is we are overestimating the interaction energy, and the reason being that another segment, let us say if I look at a particular segment, it cannot be the case that the other segments are uniformly distributed, of course the next segment has to be the close, but if I go farther along the contour, they have to be farther from this particular segment. There is no way that we can have a uniform distribution of segments around it. So, we always overestimate excluded volume from what it should be. Okay. Now, as I have already alluded to earlier, Flory was very lucky in the sense that the errors that result from the underestimation of elastic energy and overestimation of excluded volume, they both cancel out perfectly for, I would say, very mystical reasons, and he was able to get the correct scaling law. Okay. So, if I take this particular approximation, now I can write my interaction energy, also assuming that the first term is the dominant term here. This will become so I will first approximate as only the first term in the Virial expansion, and then I will use the idea that the concentration is assumed to be uniform. So, in that case I can replace the integration over dr by the volume, and volume in this case is scaling like r cube, and then we of course have V k b t, and then C is approximated as C tilde, which is m by r cube squared, and so this gives me something like V k b t m square by r cube. Again we drop the prefactor 1 by 2 since we do not care about the prefactors in the scaling law. So, now we are left with the elastic energy and the interaction energy both scaled in this particular way in terms of m and r. M is the number of segments, r is the size, and I can write the total energy as, I should use scaling as we have just derived previously. Okay. So, now we use the idea that the chain will like to minimize its energy, that is a standard thermodynamic approximation. Things like to go towards the minimum of free energy, and I can do that by taking a derivative with respect to r. The size will be such that will minimize the free energy, and that we can get by dou u by dou r equal to 0, which gives me this, and if I solve this, again dropping the prefactors, what I get is r to the power 5 scales like V m to the power cube, and so r scales like V to the power 1 by 5 m to the power 3 by 5. Okay. So, this is the scaling we have been after, or we can say r square goes like m to the power 6 by 5. If I compare that to ideal chain, it was r square going like m. In this case, we get a higher power, meaning that the chain will be more stressed compared to the ideal chain. Okay. So, this is what we have got for the good solvent case. Now, let us see how things work out for the bad solvent case. Okay. So, for the bad solvent case, now the V is actually less than 0. Okay. So, now in this case you can see that the V to the power 1 by 5 will give you an imaginary answer, okay, and that is where you can find that the R cannot be imaginary because the size has to be a real number. So, something goes amiss in the derivation, and what went wrong really is that we have missed the 3 body interactions that can be important for the collapsed chain, for the simple reason that if the chain is like collapsed, there is more possibility of 3 body interactions or 3 body contacts than compared to the case when the chain is stretched. Okay. So, we will now try to include the 3 body interactions and then see what kind of scaling laws we get here. So, again I want to point out before going further one important thing here, that whatever approximations we are making in a sense are motivated by experimental results or some kind of a physical intuition. So, although it may seem like some sort of arithmetic manipulation, it can be verified or it should be verified by some experiments or the physical intuition that we have, and only then the scaling theory can succeed. Okay. So, it is not always that whatever assumptions we have made will succeed in the representation of system, and then we have to go back and revise our estimate, because essentially what we have been doing is trying to revise or approximate or simplify the rigorous integrations that we had earlier derived, that also had certain assumptions present, but we have further simplified by simply dropping the integration and choosing to do a pure scaling analysis. So, in that sense we have to be very careful that we do not go wrong in the intuition that we started with, or we should always plan to do experiments to back up our theory, and indeed that has been done by Flory by experiments as well. So, we will return to this case of V less than 0 in the next lecture, where we also will include the 3 body interactions that we have missed earlier in the good solvent case. Thank you.